Hello everyone, welcome back to this ARSET webinar series on Introduction to NASA Snow and Ice Data Products and Applications, Part 3. This is the concluding session of this series, and today we will focus on monitoring mountain snowpack and prediction of water availability in the western US for water resources and disaster applications. Our guest speakers today are Dr. Karl Rittger and Dr. Fleming. I will be introducing them shortly. We will start with a very brief review of Part 2. So in Part 2 last week, we focused mostly on snow data discovery and access by using different tools, starting from National Snow and Ice Data Center. So we had an overview of NSIDC where more than 1400 datasets are available freely. And we also saw tools such as NASA Earth Data Search and Appears. We had demonstrations of how to discover data and subset them spatially and temporally and extract them. Then we had a demonstration of how to download data using these tools and analyze them in QGIS. There was a case study used in Grand Mesa in Colorado. For this area, snow data from SnowX, Airborne Snow Observatory, and Moody's Normalized Different Snow Index were downloaded and analyzed in QGIS. Today's session is going to focus on the application of snow data, and that is monitoring mountain snowpack and prediction of water availability in the western US for water resources and disaster applications. This is a joint session between ARSET and NASA's Western Water Action Office, or WWAO, and so the focus is going to be on the western US case studies. Just to note that the homework is posted today on our website, and it is due on August 21st. Those of you who attend all live sessions and complete the homework assignment by the deadline will receive a certificate of completion. So that just a note that the homework is available today. Starting with today's session, the overall objectives for Part 3 are that participants will be able to recognize the importance of water resources and impact of snow data in the western US, identify methods to monitor and visualize snow cover, snow albedo, snow darkening, and snow cover duration in the western US, and finally recognize how snow data are used in water resources management and forecasting snow-fed river flow with case studies in the western US. So the outline for today is that Dr. Rittger will start with monitoring mountain snowpack and demonstrate Snow Today website, and Dr. Fleming will be talking about application of snow data for water supply forecast. Before I introduce our speakers for today, here's a note about asking questions. As I mentioned in the previous sessions, please put your questions in the questions box and we will address them at the end of the webinar. Feel free to enter your questions as we go, and we will try to get to all the questions during the question and answer session after the webinar. The remainder of the questions will be answered in the question and answer document, and that will be posted on the training website about a week after the training. With that, I want to introduce our speakers for today. Dr. Karl Rittger is a research associate at the Institute of Arctic and Alpine Research, or INSTAR, where he works on projects sponsored by NASA, NOAA, and USGS, focusing on research, application, data archiving and distribution, and capacity building. His research areas include mapping snow and ice at a spatial scale suitable for mountainous terrain and large-scale, physically based distributed modeling of snow. Dr. Rittger leads the Snow Today team at the National Snow and Ice Data Center, providing real-time information for users. He is a Moody's and Weir's Land team member and executive board member of the Snow International Working Group and participates in multiple NASA working groups on snow. Our second speaker will be Dr. Fleming. Dr. Fleming is the science lead for the NASA Western Water Action Office, supporting practical application of NASA Earth observations in the western US for water resources management. His research interests include hydrology, cryospheric science, climate, data analytics, and machine learning. Dr. Fleming is also an affiliated faculty at Oregon State University in Center for Earth, Ocean, and Atmospheric Sciences and the Water Resources Graduate Program. He participates in senior level advisory activities in multiple organizations, including Water Resources Research and World Meteorological Organization Commission for Hydrology. He contributes science-based guidance to policy formation, evaluating draft legislation, and performing environmental impact assessments. So we first invite Dr. Karl Rittger. Karl?
Okay. Hi, everyone. I'm Karl Rittger at the University of Colorado Boulder at the Institute for Arctic and Alpine Research. I wanted to thank NASA for the invitation to speak in the introduction, as well as all of you for being here today. I've been working on snow monitoring for about 15 years, and a large team of folks have contributed to both algorithm development as well as the Snow Today website that I'll talk about. Mark Raleigh and I founded the Snow Today website in 2020, and critical validation and development efforts have come from Doctors Palamaki, Baer, Skiles, and Jeff Dozier, who passed in November of 2024, who was the pioneer of this research. Our community will miss him. Here's an outline of today's training presentation. First, I'll talk about an approach called spectral mixture analysis, or SMA, which can tell us the snow cover as well as other snow properties like grain size, snow albedo, and snow darkening. Walt Meyer introduced SMA earlier on the first day of training, but I'll discuss the snow signal, these algorithms, as well as the validation. After that, I'll show our analysis platform called Snow Today, which allows users to view snow properties in context with the historical conditions, and it also provides links to download that data for your own use. After that, I'll briefly show 3 examples of research to practice with data use, our plans to extend spectral mixture analysis to new sensors and regions, and then I'll follow with my vision of the future of optical remote sensing and conclude with a summary and data access. So to get started on snow signal and methods. So these graphs show the spectral signature or spectra of various things that cover the Earth's surface. On the y-axis is the reflectance or fraction of the sun's energy that is reflected by the surface. On the x-axis is the wavelength. The left side of these figures shows the visible wavelengths where our eyes can see, and in the center are near infrared wavelengths, followed by shortwave infrared wavelengths on the right. On the upper left graph, 4 vegetation spectra are shown, and those are highly absorptive in wavelengths like blue, but vegetation's highly reflective in the near infrared. So you can see where it goes up there. On the upper right is snow, which is bright in the visible wavelengths, which is why our eyes see it as white. And the 4 spectra here show fine to coarse grains, with new snow or small grains being the brightest. Near-infrared reflectance is lower for large grains, where light is more easily trapped in those larger grains. And in the shortwave infrared, snow is dark. On the left side, at the bottom, are soils, which are dark in the visible, but brighter in the near-infrared and shortwave infrared. On the lower right, you can see where multispectral satellites, such as MODIS, measure these spectra, and those are those vertical lines. And that's where the satellites are measuring these different Earth surfaces from space. So spectral mixture analysis models are physically based, meaning they use all of these data, these spectra, instead of an index like the Normalized Difference Snow Index, or NDSI, which you saw earlier in the training. The Normalized Difference Snow Index, or NDSI, subtracts the dark band in the short infrared from the bright band in the visible and normalizes it by the sum. And that can be useful for detecting snow, but it's shown to vary in accuracy, especially across regions with different vegetation types or grain sizes. In contrast, the spectral mixture analysis relies on linear combinations of M members to determine snow cover, snow grain size, and snow darkening from light-absorbing particles and snow albedo as well. This graph on the right also shows the impact of snow darkening, which is caused by light-absorbing particles on the snow surface, such as dust or carbon. And this example shows different concentrations of dust that impact the visible wavelengths. So we also detect this snow darkening. And when we multiply the snow darkening by the incoming solar radiation, we get a number in watts per square meters, which tells us how much extra energy is added to the snowpack, contributing to snow melt. So I've worked on two SMA approaches. One is the spatially and temporally complete, or STC, SCAG, and DRFS, and the other is the Spires approach. And in my slides today, you'll see data from both methods. While both are spectral mixture analysis methods, they differ. For example, the SCAG method uses snow, vegetation, and rock end members, which we saw on the last slide, while Spires uses only snow end members and uses a mixed background end member, which are combinations of other surfaces like vegetation and rock. The SCAG model runs iteratively for each pixel, while Spires groups pixels to speed up the processing. Another difference is that Spires solves simultaneously for the snow darkening or the concentration of the light-absorbing particles, while the STC SCAG DRFS model solves the snow darkening separately. Both algorithms use persistence of the surface to separate clouds, but Spires has a machine learning algorithm to help as well. The SCAG and DRFS algorithms are being adopted by the National Snow and Ice Data Center, Distributed Active Archive Center, and we have a plan to transition the STC algorithm, which gap fills them as well. Spires, on the other hand, is run by a team at Instar, giving us quite a bit of flexibility, and other groups are beginning to run this algorithm as well. Published literature shows that spectral mixture analysis methods, like the two I just showed, perform the best for snow cover over other methods like NDSI. In the left panel, back in 2013, we showed how the ModSCAG model maintains accuracy over various vegetation types. We have forest, shrubs, grasslands, and barren areas here. And I apologize, I'm missing the y-axis on these graphs. But what you would see is differences in the snow cover product minus the validation that we're doing there, which you can sort of see in the Y label. So in 2018, Dr. Mason did some similar analysis and again showed that spectral mixture analysis methods perform better than NDSI with some independent validation. And he compared 5 different algorithms. 2 of them were spectral mixture analysis and 3 were NDSI approaches in 3 different regions, the Alps at the top, the Pyrenees in the middle, and Morocco at the bottom. The graphs show the root mean squared error. More recently, on the right side, work led by Timbo Stillinger used LiDAR from the Airborne Snow Observatory, which was also introduced earlier in this training, and again perform the accuracy of the spectral mixture analysis methods over the NDSI methods. This analysis looked at different canopy covers, different view zenith, which is the angle that the satellite's looking at, and different snow cover fractions. And overall, the SMA methods perform the best. However, I should note that SMA is not available globally currently, and the Mod 10 NDSI products presented earlier in this training are very useful for this purpose. Published literature also shows that spectral mixture analysis methods perform the best for snow albedo. In 2019, work led by Dr. Baer showed that the accuracy of the remotely sensed albedo from the STC SCAG DRFS method outperforms snow aging models that are often used to estimate snow albedo. These models assume a decrease in snow albedo over time and can include estimates of dust if available. The graph on the left shows both the remotely sensed albedo and the modeled snow albedo from bats compared to the on-the-ground measurements. you can see the spectral mixture analysis retrieved albedo in blue circles falls closer to the 1-to-1 line than the red circles from the BATS model. This year, Dr. Palomaki led a paper showing how snow albedo from spectral mixture analysis performs better than 3 standard MODIS products. This figure is on the right. The 4 graphs show the bias and root mean squared error on the left and the right sides for both snow fraction and time on the top and the bottom for the 5 products that are represented by 5 lines here. The 3 spectral mixture methods in red, purple, and green outperform the standard methods in blue and orange. Notably, spectral mixture analysis performs better for full covered snow pixels, where you might think that some of the other methods would do just as well since there's little vegetation or soil. With a robust understanding of the accuracy of spectral mixture analysis methods applied to coarser 500-meter MODIS data, we're now looking at applications to higher spatial resolution 30-meter data. On the left side, we see 2 spectral mixture analysis maps of grain size, and one of them is from the Spires model and one's from the SCAG model. The SCAG model shows quite a bit of variability, where in contrast, the Spires model is showing little variability across the image for these Landsat data. When we look at the distribution of grain sizes across aspects, the box and whiskers plots on the right show that the southern and eastern aspects from the SCAG model have larger grains. This is represented by that larger extent of those blue boxes for the east and southeast directions. And this makes sense because those slopes receive more sunlight than northern facing slopes. So we're still investigating the accuracy for this Landsat scale data. Next, I'm going to move on to visualization and analysis from our Snow Today website. While the Snow Today website started in 2020, in 2024, it was added to NSIDC's homepage along with their well-known sea ice and ice sheet products. Along with a redeveloped desktop application, traffic to our site increased by 10 times from about 300 people a month in previous years to over 3,000 per month. This year's interest peaked in November and boosted our site views to about 8,000 per month. With the primary US focus in the past, most of our users are coming from the United States with some interest from other countries. And we've developed data sets for other regions, which we hope to add to the website in the coming years. Snow Today provides accurate, daily, gap-filled, 24-hour lag, 500-meter spatial resolution snow cover and snow surface properties for water managers, scientists, and the public. Snow radiative forcing, which tracks the impact of light-absorbing particles like dust and carbon on snow, impacts the snow albedo, and has only been previously produced for scientific studies, but on Snow Today, we produce this in near real time, along with the snow cover and snow albedo. While the gridded data is useful to both researchers and operational managers who have technical skills, for those without funding or skills to manipulate the data, Snow Today provides that. We'll get to that in a moment. Now, water managers need consistent products, and we've been providing those for 5 years. I won't go into a lot of detail here, but this shows the progression of our algorithm development. The Snow Today website, again, started in 2020, and we've been active for a few years now. In the first year, we used MODIS Terra and the STC SCAG DRFS algorithm. And we did that for about 4 years. Moving forward, we've now transitioned to the Spires algorithm. During the years with the STC algorithm, we made a bunch of improvements, which are highlighted at the bottom here, including the validation, which I've shown already. Currently, we're using the Spires algorithm, and we've updated this from the published version by Dr. Baer to now do near real time. We've added radiative forcing, and we've sped up the algorithm and corrected issues that we found in the original algorithm with the grain size and albedo. Looking forward, we're again parallelizing this algorithm so we can run it over larger areas and get data out faster. The daily snow viewer on Snow Today can be used to view all of these variables, and the automated analysis allows one to compare the current conditions to historical ones for states and multiple levels of river basins. This summary graph on the right shows the snow cover for this year in context with the previous 24 years for the western US, with the min, max, and interquartile ranges displayed. Snow-covered area peaked a bit later this past year than usual, which you can see by comparing the blue line to the gray shaded area. Late season snow is captured in mid-May, which can be seen by the slight increase at the end of the blue line on the right side. In addition to these graphs of snow cover, we provide similar summaries for snow albedo, snow radiative forcing, and snow cover duration. That can be seen here. Again, this figure shows snow cover, snow albedo, snow radiative forcing, and on the far right side, snow cover duration. And this is for the state of New Mexico this year, and the same date as the previous graph. This year was very dry in New Mexico, the driest on record, which you can see on the left bottom graph summarizing the snow-covered area over the year. In column 2, you can see the lack of storms in the early season created snow with low albedo, with the big dips in the blue line. Small high elevation storms likely kept the snow that did exist relatively bright after that. In column 3, we can see the snow radiative forcing. In the US West, snow radiative forcing can have a major impact on melt timing. Dust storms darken the snow, and while it's covered with new snow during the winter, it accumulates on the surface during the spring melt and accelerates the melt. In column 4, you can see the snow cover duration, which is calculated by summing the snow cover each day, and that's also very low in New Mexico this year. That was a summary for a state in the western US, and I'm now showing a summary for a basin, the Upper Colorado River Basin. This is a Hydrologic Unit Code 2, or HUC2, the Upper Colorado River Basin. This year, snow started falling in line with normal patterns, which you can see with the blue line on the left bottom there. From December to February, there was less snow cover than normal. And this also can be seen by looking at the snow cover duration in the fourth column. In column 2, you can see some dark snow in March and April from the lack of storms, and also that dust accumulating on the surface, which you can see in the radiative forcing in column 3. In addition to the HUC2 basins, currently the Snow Today website can also analyze Hydrologic Unit Code 4 basins, which are quite a bit smaller. And this figure shows the snow surface properties for the Colorado headwaters, which had near normal conditions in terms of snow cover, as shown in column 1, and snow cover duration, as shown in column 4. But you can see the same dark snow in the albedo and radiative forcing columns 3 and 4, as we saw in the previous slide for the Upper Colorado HUC2 basin. During the winter, we also write monthly articles on snow in the West. The figure at the bottom left here shows a monthly figure, and this one actually is the maximum snow cover date. So when did snow cover reach a maximum value? The red dot shows that in 2025, it was relatively late in the season, well above the mean line around January 15th. On the upper right, you can see net changes in snow water equivalent, which are displayed also on our website. We get these data from the NRCS and do analysis on those as well to pair with the remotely sensed data. We also do difference maps to show anomalies or differences from normal, which is shown here as the snow cover days map. So those red areas had much shorter duration. You can see down in New Mexico a lot of red, which I've shown earlier. And some of the northern areas are blue, so showing they had much longer snow cover duration than normal. We write these articles once a month, usually from February to June, as a retrospective on the previous month. All right, so now we'll move a bit to some examples of this data in use. The first example of the use of Snow Today data is from the NRCS, which runs an operational US West-wide water supply forecast system each day. And this study, snow cover was considered alongside the traditional SNOTEL or snow water equivalent point measurements in both the statistical and AI-based models. The addition of the snow cover results in accuracy gains for late season forecasts as snow lines rise above the in situ measurement sites. Snow cover similarly improved accuracy for early season forecasts, which are also problematic. Overall, there was a 10 to 25% improvement in the forecast, and the gains were roughly proportional to how thoroughly runoff is dominated by snowmelt compared to rainfall, and how poorly in situ measurements monitor the late season snowpack. Additional exploration suggests that snow cover, as the sole predictor, can yield reasonable water supply forecasts for mid to late season. So potentially useful in sparsely monitored regions. Sean Fleming will review this work in more detail, I believe. Another application of the snow cover products are in the CU Fusion West-wide SWE product. This work, led by Noah Mullich, uses a generalized linear regression model to estimate the snow water equivalent on a weekly forecast schedule during the snow season. I won't go into too much detail about this since our focus is on the remotely sensed product, but these snow water equivalent products are available starting in February of each year, and you can find those at Instar. Another example of our use of data is from the Colorado River Basin Forecast Center, or CBRFC. They use a temperature index model called Snow 17 to estimate snowmelt, and that relies on snow cover along with air temperatures and degree day factors. There's a very simplified equation at the top left here. The figure on the top left is a conceptual figure showing the impact of factors like solar radiation and albedo on the degree day melt factor. And our radiative forcing products integrate both the snow darkening and the incoming solar radiation. And CBRFC uses these data to increase the Snow 17 air temperatures to account for the dust. The graph at the bottom shows some late season dust and snowstorms captured by the radiative forcing product in 2022. In addition to the magnitude of the snow melt, which is shown on the left, the right side shows an example of zonal fractional snow cover from satellite observations compared to the Snow 17 model's snow cover. And there's a difference map shown at the bottom here. This allows forecasters to see differences between the observations from space and what their model is showing, and helps them qualitatively see if the melt is being generated from the correct locations. Next, I'll talk about extending spectral mixture analysis to new sensors and regions. MODIS, which we've relied on since 2000, is nearing end of life. The satellites drifting closer to the Earth resulting in earlier morning observations where there are larger shadows from mountains, making it harder to see the snow. The MODIS science team has proposed phasing out the data processing later this year, though Congress has stated they'd like to continue funding this data. We're still waiting on a vote for that. So we're working with our ability to extend the data through the use of the VIIRS satellite series, which will go through 2035 or 2040. VIIRS on the Tsunomi NPP platform, launched in 2011, has nearly 15 years of overlap with MODIS, opening the door for intercalibration to reach the goal of a 30-year time series, which water managers typically like to see. Similarly, with the next satellite in the series, NOAA 20, there's a 7-year overlap with the MODIS instrument. Early results from our efforts to transition to VIIRS were presented by Dr. Leonard at the American Geophysical Union meeting last year. Here you can see the viewable fractional snow cover at the top, snow on the ground, which accounts for snow under the trees in the center, and snow albedo at the bottom. Looking from left to right, from winter to summer, we see progression for snow cover and albedo as expected. Validation of these data are in process currently, and we plan to use these data alongside with the MODIS record to extend from 2000 to present. The U.S. Bureau of Reclamation is funding our work to continue advancing snow cover and albedo products from NASA satellites. Our updated algorithm includes improved new and ephemeral snow detection and improved interpolation schemes for very cloudy regions. We plan to intercalibrate the data streams between MODIS and multiple VIIRS sensors. There's a 50-minute difference between two of the VIIR sensors, which allows us to perhaps see between clouds as clouds pass by. Also, in addition to the SPIRES algorithm, the National Snow and Ice Data Center is working on a near real-time gap-filled mod-SCAG mod-DRFS product, which may come back online in 2026. Currently, we're processing data in the Western US, which is represented by the black tiles here. We've created historical data for the red tiles as well and plan these to run in near real time in this coming winter. Not shown here, we're working on data sets for the Eastern US and Canada, New Zealand, Chile, and High Mountain Asia. The Alaska Pacific River Forecast Center are partners in our work. Shown here is a progression of snow cover from March 15th, where there is near full snow cover, to June 15th, when just the highest mountain ranges are covered with snow. Collaboration with the University of Calgary on the Yukon River has motivated a validation of this data set as well. We validated using about 20 Landsat scenes for snow cover across a number of years using both the SCAG and the SPIRES algorithms on Landsat. Those are in the middle column. On the right, you can see the differences between the MODIS observations and the Landsat observations. And again, the difference is MODIS is at 500 meters and Landsat is at 30 meters. So we expect Landsat to give us better estimates of snow cover. While we do see differences, those are mostly in the vegetated areas where the models are making different assumptions. But despite those differences, the overall statistics are very high, and the fractional statistics show mean differences of about 5%, which is pretty accurate. Moving on to the future of optical remote sensing, we hope to integrate spatial, spectral, and temporal resolutions from these various satellites. Looking forward, there are opportunities in data fusion for both multispectral and hyperspectral data, which measures the spectrum in more wavelengths. These examples of snow cover fusion and snow albedo fusion are shown on the left and right respectively. For snow cover on the left, we have developed fusions based on random forest machine learning that leverage 30-meter spatial resolution of Landsat and the daily cadence of MODIS. Our recent work, published in 2024, developed a local model that uses training from the surrounding region and resulted in more accurate snow maps than both MODIS and a global fusion that was trained on full Landsat images. Currently, this is not being done operationally, but once trained, the model could be used with our current MODIS or future VIIRS data as input. Moving to the figures on the right side, while the spatial resolution of Landsat is helpful, using data from a hyperspectral sensor can also improve our albedo estimates. Spectral mixtures estimates of albedo at 500-meter resolution still have errors of around 7 to 10% when compared to in situ observations. Here we used hyperspectral data from the Airborne Snow Observatory as a proof of concept for satellite-borne hyperspectral data. The data fusion reduces the MODIS error by more than 50% of its original values and completely removes the bias when we train on data in the same basin from the same time or a different time. However, when we train the model on a different basin, the root mean squared error is unchanged from our original MODIS data. So there's some improvements to be made there. Notably, we were using airborne data here, and in the future we could use spaceborne satellite hyperspectral data, which would allow us to observe every basin. In summary, Snow Today runs accurate SMA algorithms daily with a 24-hour lag to produce gridded and summarized data in context from water year 2001 to present. Snow Today is wrapping up its 6th year of operational production this year, and Snow Today will continue in water year 2026, hopefully producing data for a wider array of regions. Snow Today continues to work on VIIRS data in preparation for the MODIS Terra decommissioning, and future improvements in spatial resolution and accuracy will be achieved through the fusion of spatial, temporal, and spectral resolutions. Thank you very much. I hope you've enjoyed this training. Before I go, I'm going to talk about where you can find the data that I talked about today. On the left side, we have the Spires-based algorithms, and on the right side, the SCAG-DRFS algorithms. And the top is historical data, and the bottom is near real-time data. And all of these data sets are available at the National Snow and Ice Data Center, with various dates for the historical and the near real-time data. I will note that the data on the upper right is not gap-filled like the other three data sets. Thank you very much.
Hi there. Thanks, Karl, for the introduction and for going over your Snow Today products. In this part of the ARSET training, I'm just going to give an overview of one, and this is just one example of how Karl's data and, of course, NASA snow data, snow and ice data more broadly, can be used in a practical water management or hydrologic science application. So we're going to use that INSTAR satellite data in a statistical and AI-based river hydrology model to show how it can be used to improve the accuracy of operational water supply forecasts in the Western U.S. There we go. So some motivation here. There's a great quote from the late Jeff Dozier from an EOS transaction article over a decade ago. The punchline was that where he saw the future, and I think a lot of us would agree, I certainly do, that progress in water supply forecasting and hydrologic prediction in general and hydrologic understanding going forward is going to reflect in large part a combination of remotely sensed snow data, particularly but not exclusively from space, with machine learning driven hydrologic prediction models. So what is, that was over a decade ago. How are things looking? So from, the 20,000 foot view looks pretty good. But if you did get down into the weeds, there are gaps. If you look at operational flood and water supply forecast systems at governmental service delivery organizations, SDOs, that's an acronym I'm going to use a few times here, you're going to see that in general, remotely sensed snow data are mainly used for qualitative guidance. In addition, most hydrologic models don't use AI. Now, in the private sector, there's some companies out there who are, but if you're looking at big organizations like USBR, USDA, NOAA, groups like that, this is generally true what I'm saying here. Also, in both research and practice, there are really very few examples of remotely sensed snow data driving AI-based streamflow models for seasonal water supply forecasting. So what we're going to do here is that in the context of literally generations old, U.S. West-wide operational water supply forecast system operated by the U.S. Department of Agriculture's Natural Resources Conservation Service. In that context, we're going to test a new remotely sensed snow data set as forcing to a new AI-driven hydrologic model. So let's step back and give a little bit of background in terms of water resource science here, what we're actually doing. So what is a water supply forecast? I've used that term a few times. So in the Western US water management, there's a set definition for this. And these are forecasts issued once or more per month during the beginning of winter, say January or so, of the upcoming spring-summer total flow volume for a given river, performed by service delivery organizations or SDOs, having strict accountabilities to end users, including the general public, around reliable forecast product generation. So that's a bit of a mouthful, but you may have come across these things. They're quite commonplace in water resource management. So California Department of Water Resources Bulletin 120 is a famous example of it. The NOAA National Weather Service River Forecast Centers, their ESPs based on a process-based model is another example, and the USDA and NRCS regression models are still another example of West-wide WSFs. So why are they important? Well, they're foundational to Western water management. They're used for all sorts of choices. I don't have time to go through them all here, but a few examples are crop selection, so they're very important to ag. Water rights rentals, they're important to the water market. They're heavily used in hydropower generation optimization and revenue optimization. There are all like very specific legal and treaty obligations that are, in management of transboundary waters that are driven very quite specifically by WSFs. So there's a whole bunch of implications of it. And if you want to try and put a dollar value on it, it's a little tough, but bear in mind that there's over $1 trillion with a T dollars of water managed annually in the Colorado Basin alone. And the ability to improve a water supply forecast, even marginally, can be valued at over $100 million a year in hydropower generation just in the Columbia Basin. So it's important to get it right and to make it better. So next question, especially if not familiar with WSFs, is how is this possible? Weather forecasts can only reliably look out, a few days, couple weeks at most. There's progress in S2S forecasting, but still we're kind of limited on that. So how can you forecast river flow volumes, looking at literally like half a year? And the reason is that there are lags between hydrometeorological forecasting and hydrologic response. So, and we're looking quite specifically in the Western US and Western Canada as well. In that region, precipitation falls mainly in winter and mainly as snowfall, especially in the mountains. And that mountain snowpack forms effectively this gigantic reservoir that produces runoff the following spring and summer when it's most needed. So snowpack data are essentially a powerful, though not the only, predictor or boundary condition in watershed hydrology models used for water supply forecasting. If you know what the snowpack is, you'll have a decent idea right off the bat of what the upcoming spring-summer runoff is going to be. There's more to it than that, but that's kind of the foundation of it. So what kind of data then do we use? Well, classically, it's in situ data. So these are manual snow surveys, and there's a photograph of one here being run by the California Cooperative Snow Survey, as well as telemetered snow pillows, such as SNOWTEL. So that's a little bit of the broad context. We'll kind of zoom in a little bit on the NRCS here. So the Snow Survey and Water Supply Forecast Program, that's essentially been run by the USDA since the 1930s, uses both manual snow surveys and that SNOWTEL network we just covered in the last slide. And it's the largest standalone operational WSF system in the West. So it uses a few different models, but the core method is principal component regression, which is a linear statistical method introduced to water supply forecasting by David Guerin in the early 1990s. But NRCS is now transitioning to an AI-based approach called M4, which stands for multi-model metasystem, machine learning metasystem. So a little bit about that. So it went operational at the NRCS, I think 2 seasons ago now. It was built from scratch in a user needs-driven framework to meet key NRCS design criteria for an operational water supply forecast model. So instead of R2O, it's kind of O2R in a way, and then back to operations, if you're familiar with those acronyms. So what is it? It's a metasystem of 6 different data-driven forecast systems that all work together, and several of them contain machine learning. So it used something called a Maya design philosophy, most advanced yet acceptable. So kind of meeting the hydrology community where they are and building what they need. Which basically took the old system and hot rodded it. There's a lot of trust in that old system, but there's also room for improvement. So we basically just threw a whole bunch of very specific useful technologies in there, including evolutionary computing, machine learning, some pretty sophisticated statistical methods, and what have you. So enough about the model. What about the data? So we're not going to go into too much detail about it because Karl's just gone over it in a good amount of detail in the previous presentation, but just more from a modeling perspective, what are we looking at here? So to reiterate, we're looking at the MODIS instrument aboard the Aqua and Terra satellites. MODIS data provides a basis for measuring snow covered area or fractional snow covered area. And it has and this is very appealing to an operational group, as a long history of use in river forecasting research and operations, both in the US and internationally. So we're using a particular Modus product here that Karl just reviewed. It's called the Spatiotemporally Complete, or STC, ModSCAG Fractional Snow Covered Area Product, SSCA. So why this particular product? It's about picking the right tool for the job. And for this job, there's certain criteria that the USDA and RCS needed. One was a long record, 20 years or more. You need to have data within the first couple working days of every month, because that's when the NRCS is obligated to get its water supply forecasts out. So that has implications in terms of fast cadence and short latency of the remote sensing product. Continuity is also important. It's nice to build a product, but it needs to keep on working going forward. So the Aqua and Terra satellites are near the end of their lifetimes, but continuity will be ensured via the VIIRS product. And of equal importance to all these other criteria, there can be no spatial or temporal gaps. That's just a big pain when you're trying to do something operationally. So that particular data set really fit the bill. Now, how did we use it? Well, we developed a total of 220 models and a relatively exhaustive set of experiments drawn from the existing operational USDA NRCS forecast system. And to be clear, I should point out that when I did this work, this was a WWAO, NASA Western Water Action Office, WWAO, coordinated project with Karl through UC Boulder, and myself when I was at the USDA. So this is, a USDA product here, though I am now at NASA. So I'll just throw that in there, just for clarity. So those outcomes obviously were interpreted from an NRCS operational perspective, with an eye to when, where, and why that satellite data improved water supply forecast skill. So what did these experiments consist of? 4 different locations, widely spaced across the Western US, with very different snow regimes, very different hydrologic regimes, quite different water management concerns. Lead times, we looked at issue forecast dates from January all the way through June. For the most part, it varies a little bit depending on where you are. For example, the Gila River in the pretty far south in New Mexico, different environment, different lead times and forecast intervals, or targets rather. Which hydrologic models did we use? We used that M4 system I just described, as well as the previous NRCS linear prediction model. And we used a whole bunch of different combinations of data, just the SNOWTEL, snow water equivalent and precipitation data as in the existing operational system, just the ModSCAG FCA satellite data, aggregated either by total basin average or averages across a series of elevation bands. I won't get into the rationale for that at this point, but I'd be happy to discuss that later, as well as various combinations, mixing and matching these things. So getting to some of the punchlines, don't worry, I'm not going to review these rather busy graphs in detail here, but just a word about how we measure the water supply forecast benefit of satellite data in the context of M4 and the version of the linear model that we used as well here. There's kind of 2 sets of metrics. One is the percent improvement in both the deterministic and probabilistic forecast accuracy metrics. So that's things like R squared, that's things like root mean square error, and it's also RPSS. One really important aspect of operational water supply forecasting is that in general, the end users of those products want estimates of the quantitative estimates of the uncertainty in the forecast, not just the best estimate, but also estimates of the uncertainty in it. So we also look at it from a probabilistic perspective. That's part of what the product generates, and we want to assess how well it does that. The other set of metrics it relates to the genetic algorithm that was used in both of these models for feature optimization or predictor selection in a more classical statistical nomenclature. So essentially, on the basis of out-of-sample prediction scale, the genetic algorithm picks which predictors to retain in the model on the basis of their ability to improve the forecast. So it's not just a kitchen, everything in the kitchen sink kind of approach. You throw in a bunch of potentially useful things, and the genetic algorithm decides which of them to keep. And looking at which of those predictor variants to keep gives you information about the value of the satellite data, whether it's retained or not. So what are some punchlines? There's some obvious things that you would expect, irrespective of what kind of data you're using. Accuracy decreases with increasing lead time. And in cases where any reasonable prediction skill exists, the AI-driven system generally meets or beats the linear model. That's not news. That had already been determined in previous work. It's part of the reason why NRCS adopted this model. Getting down to the nuts and bolts of it, though, using the combination of both satellite data and in situ data often beats just using the in situ data alone. So it's probably not too much of a surprise. In situ data is just measurements at a point in space. Even if you have several SNOTEL stations, still those are just a few individual points in space, and you're looking at the snowpack and across much of a watershed. So the satellite data fills in the gaps. But SNOTEL actually provides snow water equivalent, whereas MODSCAG is just providing snow covered area. So having the two together improves the forecast, but not in all cases. And it kind of parses naturally into 3 seasonal timeframes that I'll go over in the next slide. But just to underline the punchline here is that integration of the satellite data into day-to-day production systems for water supply forecast modeling across the Western U.S. is advisable. That's kind of the overall conclusion here. So punchlines, as I said, it kind of naturally segregated into 3 seasonal timeframes. So for short lead, late season forecasts, this is when you're getting into May and June and the snowpack's being depleted. Providing MODSCAG data alongside SNOTEL data to the model increased the accuracy substantially for most of the rivers. The degree to which an improvement was seen was, kind of roughly proportional to how snowmelt dominated the river, the spring summer runoff is in that particular river. Not surprising, and that's as opposed to spring summer rain inputs, and also how poorly the local existing SNOTEL network samples the late season mountain snowpack. As it becomes patchy or the snow line moves above, the actual in situ network. We also found that the AI system and the linear system, although the AI system generally performed better, the percent improvements that were obtained from integrating satellite data in these late season forecasts in terms of percent improvement was about the same between the 2 technologies. In the medium lead mid-season forecast, so this is around April or so, March, April, when the seasonal snowpack in the mountains is pretty much at its maximum. Neither model benefited from having the satellite data incorporated. And that's essentially a testament to how over the last century, literally, there's been so much experiential knowledge developed about how to design an in situ snow monitoring network, which is really kind of keyed around, indexing what the peak snowpack is, that adding this kind of satellite data didn't help much. Now, other kinds of satellite data around snowpack and obviously other geophysical parameters could still be useful. But we're just kind of looking at this particular product at the moment. What was also really interesting, though, is for those very long lead early season forecasts, and this is important because the longer the lead you get, the better. It's really important for things like drought planning in particular. Again, it's kind of like the short lead late season forecasts. Both models, both the linear statistical water supply forecast model and the AI-driven hydrologic model, benefited from the use of that MODSCAG satellite data. There is one significant difference, and that's not surprising. Early season, potentially patchy snowpack, potentially high snow line that the in situ, monitoring network's not going to get. There's something more complicated going on, though, because the linear models in those early season forecasts, the linear hydrologic models weren't really able to leverage that additional information, whereas the AI-driven model M4 did. And that implies that there's some strong nonlinearity and or interactions going on there that the machine learning can handle and the linear model can't. And there's some specific ideas around exactly what that looks like, but we'll just leave it at that for the moment. So there's a few other outcomes that I'll touch on briefly here. So again, our main punchline is that from an overall practical operational perspective, integrating that ModSCAG snow-covered area data into both the linear and in particular the machine learning driven hydrologic models improved substantially the quality of the water supply forecast. And that's worth a lot. And it's something that's operationally very doable. So, you know, it was a success from that perspective. But there's a couple of other interesting things that came out of the study. One is that this combination of an in situ network, a data-driven hydrologic model with a predictor selection algorithm or feature optimization algorithm in the machine learning nomenclature, as well as satellite data with comprehensive spatial coverage, can in effect support site selection for expansion of that in situ network. So what we're looking at in this graph here is a particular river, Walker River. This is on the east side of the summit of the Sierra Nevada in California, flowing into the Walker Lake Basin. Looking at the June forecast issue date. And we're looking at 7 different elevation bands here, this meters above sea level. I just want to emphasize that the details vary between watersheds and lead times. This is just a particular example we're looking at here. And this bar graph shows, I won't go into the details, we don't have time, but essentially it shows the degree to which M4, the AI-driven system, or principal component regression, the linear system, wanted to use the satellite data. So what we see is that at the intermediate elevations, kind of mid elevations in the watershed, the linear and machine learning models both really want to use that satellite data. What that suggests is that, and remember, this is all in terms of the accuracy of a water supply forecast model, which is ingesting and conditional on the in situ monitoring network. So what this is essentially telling us is that it would be beneficial if we had an additional SNOTEL station at these mid elevations for spatial gap filling, essentially, as the snow line is either, you know, right. Well, in this case, it's a June forecast, so you know the snowpack's starting to become a little bit patchy. What we're also seeing, particularly in the machine learning model, is it's also retaining high elevation band satellite data, you know, over 3,000 meters there, which suggests that M4 is also using the satellite data to essentially chase the snow line uphill. So it also makes sense then to have a higher elevation SNOTEL station up there if you were looking to improve your in situ network, which NRCS is, because they're also responsible for running the SNOTEL network. On another note, you know, it was kind of interesting to see, well, what if we don't have the opposite end of the spectrum? What if we don't have an in situ network at all? How good can we do just using the satellite data? And this is a particular example from the Piedra River in the southern part of the upper Colorado River Basin, watershed, headwater watershed up there. We're looking at the nonlinear model, the AI-based model, you know, vaguely, roughly similar results for the other models and other locations to varying degrees. And what we see is that, yeah, you know, unsurprisingly, having that in situ snow water equivalent information does help, but just using the satellite data, you can get some pretty, you know, serviceable R squares in your, you know, these are out of sample results for water supply forecasting, and you can get some pretty good results pretty early in the season, certainly by March or April in particular. just using that satellite data. So that is potentially a useful thing to have in your pocket if you're working in some very remote areas or historically underserved areas, perhaps international development contexts, things of that nature, where these very pretty expensive, not so much to install to some degree, but also to maintain these in situ networks. It can be tough to keep them going, keep them working well, all the support around, the data QC and storage and dissemination, all that kind of stuff. Whereas you can just pull this NASA data basically off the internet or from Karl in particular, using his refined product and his data distribution systems and get a pretty darn good result. So I'll wrap it up with that. I would be happy to take any questions. And if you're interested in learning more about this particular example, it was published in an AGU Water Resources Research article that's free and open access, as is the code. So with that, I'll close it out. Thank you for your time.
Thank you so very much, Karl and Sean, for your excellent presentations. Just to summarize what we saw today, we reviewed two spectral mixture analysis or SMA approaches to determine snow cover, snow grain size, snow darkening from light absorbing particles, and snow albedo. These two methods are spatially and temporally complete snow cover and grain size or STC SCAG and snow property inversion from remote sensing or SPIRES. As Karl mentioned, both these SMA methods, they are more accurate than normalized difference snow index. Then we talked about Snow Today. Snow Today runs accurate SMA algorithms daily with 24-hour lag to produce gridded and summarized data in the context for water year 2001 to present year and focuses on the Western US. And it will continue working on WIRS data in preparation for Moody's Terra decommissioning in near future. This is the site. We had a demonstration of Snow Today. Then we saw application of STD ModSCAG for water supply forecast or WSF. We saw an overview of multi-model machine learning metasystem or M4 model for water supply forecast using STC ModSCAG snow fraction and SNOWTEL snow water equivalent data. And results indicate that integration of STC ModSCAG fractional snow cover area for WSF modeling in the Western US improves the forecast in most cases compared to SNOWTEL data alone, particularly for long lead early season forecasts when M4 is used. For basins where the spring-summer runoff is dominated by snowmelt, using ModSCAG with no in-situ data may provide serviceable short and medium lead water supply forecast. That's a very important point where there are not sufficient in-situ data. This brings us to the conclusion of today's session as well as this webinar series. And we just want to summarize what we saw in these three parts. We started by looking at importance of snow and ice. They play a crucial role in Earth's water and energy cycles. Snow stores water for days to months, while ice stores water for hundreds to tens of thousands of years. And then we focused primarily on snow data products and properties, and we really did not talk much about the ice products in this webinar series for two reasons. First, the focus was mostly on a shorter time scale where snow melt and snow water equivalent contribute to water supply. And then there is a lot more information about land and sea ice that we plan to do in future. So we focused on these snow products and properties, snow covered area, snow thickness, snow water equivalent, and snow albedo, grain size, and impurities. And then I also want to point out that ARSET did conduct a training on sea ice using SAR, and the link is provided here for your information. and we will offer a separate training on land and sea ice products in the near future. We reviewed remote sensing missions and sensors. So for different temporal coverage and spatial coverage, they provide snow data. We saw that passive microwave and visible and near infrared spectral measurements are used, and for your reference, satellites and sensors are listed here with their corresponding temporal coverage. We talked about snow data products, so snow cover and normalized difference snow index available from MODIS and WIRS at multiple spatial and temporal resolutions. We talked about snow water equivalent available from AMSR-E and AMSR-2, and improvement to standard MODIS snow products by using MODSCAG, TRFS, and SPIRES. We saw that also. And then talked about airborne data from Airborne Snow Observatory and SnowX products. NSIDC provided an overview of their website as well as tools for data search, temporal and spatial subset, and download by using Earth Data Search and Appears. And we had snow data analysis and visualization using QGIS. Example here is shown for MODIS NDSI, and this is ASO and SnowX snow depth, focusing on Grand Mesa in Colorado as a case study. We saw several applications of snow data. We saw monitoring variability of snow in Alaska for National Petroleum Reserve of Alaska and Arctic National Wildlife Refuge for decision making, which used MODIS snow cover and also SWE data. Then we saw Snow Today, monitoring mountain snowpack, and there are several applications of that, of STC MODSCAG. In particular, we saw water supply forecast using M4 for Natural Resources Conservation Services. Then we saw real-time snow water equivalent derived from fusion of fractional snow cover area and ground-based snow water equivalent, and assessing snow melt for Colorado Basin River Forecast Center. This brings us to the end of today's presentation, and before we conclude today's session and go to question and answer part, here is one more NASA web tool that we thought would be useful to know about, and that is NASA Worldview. This tool allows near real-time and past data exploration and visualization. It allows searching for a variety of NASA geophysical data products, including some of the snow data products we saw during this webinar series. And so what I'm going to do is quickly show this tool, how to use it, so that you can explore at your own convenience. I'm going to share my screen and go to this tool. This is the Worldview site, and once you go to this website, you will have description of the site, as well as you can look at several case studies to learn more about Worldview features, and these are tutorials, but basically it allows visual exploration of past and present satellite imagery for a variety of data sets. Here this eye allows you to explore more features, and here you can start using Worldview. That's what we're going to do, and look at some of the snow products we have looked at earlier. Here on the left hand side you have several layers. Reference is so you can turn these layers on or off by clicking here. So these are place labels, these are coastlines, borders and roads, and these are base layers. These are true color images from WIRS and MODIS from different satellites, and the one that's shown here is from Terra MODIS. This is a true color image. You can see land, ocean, clouds, etc. You can turn that off and on, and these layers as well. Here's the timeline to explore data from near real time to past data, and you can navigate by clicking on this arrow or by changing dates or months or years. And so this is the time selection bar, and let's go to winter season, so we can look at snow products. Okay, now to explore different data sets, you would go to add layers here and click on that, and this opens this window with a number of options by thematic areas. You can search different parameters, but let's focus on snow. When you type data that you're looking for, it searches and provides a list of all the data sets available for that particular parameter. So here you see a number of snow parameters. Let's look at what we saw earlier from Terra and Aqua Modis. So here you can see normalized difference snow index, or NDSI, from Terra Modis, from Aqua Modis, and of course there are monthly and daily data. As you go down, this is snow extent, snow cover. Again, this is from NOAA 20 WEIRS, and this is snow water equivalent from ARSET 2 that we saw earlier in part 2 of this webinar series. So to select these layers, I'm just going to show a couple of examples. So let's start with Terra Modis NDSI, and we can pick daily data here. So this is NDSI. Click here to select the layer, and that is visible now on this map that we'll look at. If you click here, you will get information about this product and appropriate reference for that product. Let's look at one more parameter, and that is snow water equivalent, again daily from ARSET 2. You can turn that on, and if you see this symbol, that shows that you can do a time series in addition to map. So let's look at the maps first. Here you can see that you have snow cover, or NDSI, and that's from 1 to 100. This is Terra Modis, and this is ARSET 2 snow water equivalent in millimeter. You can turn the base layer off just for clear view of snow, and let's even turn snow water equivalent off. So this is NDSI for 1st of January 24. Let's go to 25. So here you can zoom in to the region of your interest. These are global data, so you can zoom into other regions as well, especially in the northern hemisphere winter. You can see the snow in the higher latitudes, and at higher altitudes you can explore that. You can turn snow water equivalent data on, and as you can see now, this is the scale, and you can move this layer also. So let's see. Yeah, you can move, so you can clearly see NDSI and snow water equivalent. Each of these layers can individually be customized, different transparency, different color options, and different thresholds or values can be chosen, and you can look at tutorials to learn more about that. But basically, we wanted to show that you can quickly explore a number of data sets, and you can visualize. Here there is animation feature. You can select, so this is 1st January to 11th January. You can change range here, time range here, and then animate data. And you can see that data are animated. You can see how snow features are evolving during this period, and you can do this for longer time period as well. So this is a very nice tool that allows you to explore and visualize data. And if you go to data download here, after viewing and selecting what you want, it again takes you back to NASA's Earth Data Search, and then you can follow the procedure that we saw earlier in the webinar series, how to download the data. But this is a nice way to look at the different parameters simultaneously. Just a note about homework once again. It's posted today on the training webpage, and answers must be submitted via Google Forms. It will be due on 21st of August, and certificate of completion will be awarded to those who attended all 3 live webinars. Complete the homework assignment by the deadline, and the certificate will be sent to you via email approximately 2 months after completion of the course. With that, we really want to thank all our guest speakers for sharing their expertise and contributing to this training webinar, especially National Snow and Ice Data Center and SIDC and Western Water Section Office, WWAO. So specifically, we had our speakers, Andrew Barrett, Walter Meyer, Ryan Thurer, Michaela Big, Saber Brescher, Diane Fritz, Karl Rittger, and Sean Fleming. Thank you all for your contribution. And as we go to the question and answer session, please feel free to provide any additional comments you have. This is ARSET contact information for us, and this is ARSET website and YouTube link for reviewing all the presentations, and recordings will be posted there as well. Also, join our quarterly newsletter to stay up to date on our latest training. You can send an email to this address with no subject line and follow the instructions sent in response, and you will join our listserv and receive information about upcoming ARSET trainings also. Thank you all very much for attending this webinar series, and we will go to the question and answer session now. Start with our question and answer session, and thank you again to all our guest speakers and to all of you for attending today's webinar session. So to start with question 1, we'll go through a few questions here. Question 1, how does grain size estimated from the SCAG model compared to grain size derived from Landsat OLI data? And is there a known method or empirical relationship to convert Landsat derived grain size estimates to actual in situ grain size measurements?
This is Karl. I'll go ahead and jump in here. So just to clarify, SCAG is a model, the snow covered area and grain size model, that can be run on any multispectral satellite data. So, the ones that we typically do are from MODIS or VIIRS, those daily estimates, and Landsat is higher spatial resolution. So presumably we could get slightly more accurate answers from Landsat. But to date, I'm sort of unaware of anyone who's actually compared grain sizes across satellites. I think it's definitely something important to do as we move to fuse the higher spatial resolution data to the higher temporal resolution data. And I guess in terms of comparing to in situ grain size measurements, I think some of that work has been done. The main difference is that the grains that you're measuring in the field might not be spherical, which is the assumption made in the model. So you could see some differences because of different grain shapes. And the I guess other models that I talked about, Spires, but also a sort of simpler NDGSI or normalized difference grain index can also be used to estimate grain sizes. So there's a few different ways to do that, and you might see differences based on the grains or on the shape of the snow grains. I'll go ahead and just move on to question 2. So is snow today only for the lower 48 states? What about Alaska, Canada? So we've got the system working really well for the Western United States, and we started producing data for Alaska and Canada that we hope to add to Snow Today before sort of the next snow season gets going. So we're sort of validating that data. In Alaska, there's quite a bit more cloud cover than many parts of the Western US. So that's a challenge. So we've made some edits to the Spires model to try to account for that. So yeah, stay tuned. Please check in. Feel free to contact NSIDC or myself about those data sets, which we hope to publish in the coming months.
Thank you, Karl. And question 3, which snow parameters are measured in field campaigns and what are typical tools for those measurements? What temporal and spatial frequency do we typically get from such measurements?
All right. Well, this one we could probably talk about for quite a while. I did write down some things here which I might expand upon when I have a little bit more time. It sort of depends on the field campaign and what the goals are and who's funding that work. But I would say the most typical information sampled is the snow water equivalent. Manually, that's done through digging snow pits where you measure both the depth and the density of the snow throughout the column. And that's a very accurate way to measure the snow water equivalent. And typically, water supply forecasters, think snow water equivalent's the holy grail of snow information. So this is why this measurement's done most frequently. Federal samplers, which are tubes that can also be used to more quickly measure the snow water equivalent, are also used. That's just faster than digging snow pits. The NASA SnowX campaign was one of the largest field campaigns in recent history, and NASA supported the ClipX field campaign before that. So these are two really large field campaigns. In the most recent SnowX, they did measure snow water equivalent with LiDAR and radar as well. And this is in an effort to sort of prove the technology and algorithms so we can move to a space-based estimate of snow water equivalent, which we currently do not have. Snow wetness or snow water content is also something that people are interested in. It can tell you whether the snow is melting. So that can be done using lysimeters. That data, I'd say, is probably few and far in between. Often the energy balance is measured. So this involves sort of different sensors on the ground that can measure incoming and outgoing shortwave and longwave radiation. The other two components of the energy balance often used are the sensible and latent heat, which depend on air temperature and vapor pressure. So often those are measured if possible as well. In alpine environments, it's the solar radiation driving most of that snowmelt and energy balance. But in forested areas or high latitude areas, other components can become much larger. So yeah, I guess that's the main things that I can think of. I provided some links to the SnowX campaigns and data at NSIDC from that. NSIDC also has the ClipX or CLPX data sets from a really large field campaign.
Yeah, thank you so much. This is very informative. And then question 4 also is to follow up. How much of a limiting factor are these field measurements on greater watershed models?
I had hoped Sean might jump in here for this one. I'm not sure if he's here. I do less of the watershed modeling. I think point measurements have been used, let's see, for a really long time. Sean, do you wanna take over on this one or?
Yeah. So it depends what you mean by field measurements. So if you're referring to in situ measurements from ongoing monitoring networks, if that's what the question is referring to, then we're talking about the things that Karl just mentioned. So that's primarily manual measurements using that federal sampler. Which is actually quite effective and accurate way of doing it, but it can only be done maybe once or at most twice a month, just because of the logistics of getting up into the mountains and actually doing that. The primary source of data used in watershed models on Snowpack conventionally is from telemetered snow pillows. So across most of the U.S., that's SNOTEL, which is run by the U.S. Department of Agriculture. In most of California, that's the California Department of Water Resources. In Canada, there are other groups that do it. It's also done in Western Europe by various groups operationally. So those provide actually really good information that's quite hard to beat in terms of the kinds of practical, pragmatic things that one would typically look for from an operational streamflow model. And part of the reason for that is that there's been literally like 100 years of experience using these things and knowing where to take those measurements. So to take a step back, snow tail measurements and what California Department of Water Resources does and what other agencies do in terms of their telemetry data. That's so. For those of you who don't know, I have no idea what your level of knowledge about this is or isn't. So I'll just go through it. A snow pillow is basically like a balloon almost. And it's filled with antifreeze and that's hooked up to a transducer, and it's just sitting there on the mountain, essentially weighing how much snow is on top of it, and then sends that data back on a very frequent basis. So you have a really temporally high resolution data record. So that having been explained, there's been a long track record figuring out where to put these snowtail sites or these manual snow survey sites. It's typically kind of mid-elevations, forested areas with a little bit of a clearing. And just on the basis of working that out over the last 100 years, they found ways, these kinds of siting protocols lead to data that serves as a pretty good index for the total amount of snow water equivalent in that watershed. Particularly, at the peak, which is, in the Western US, it's kind of March, maybe early April, something like that. And then simply using that data in watershed models really works pretty well. But we're really bumping up against some limitations to that. So you don't know what's happening in between these in situ stations. And that becomes particularly problematic if the snow cover, like early and late in the season, when the snow cover is patchy, or when the snow line's above the snowtail site or above where the fixed manual measurement site is, in which case you have absolutely no information about snowpack. So that is where remote sensing becomes a really, really powerful tool. And basically whenever it's added to, and it generally is used in addition to those in situ measurements, it really, really helps with the watershed models. And it's also really important for more fundamental scientific research that you might do using these watershed models to really understand detailed watershed processes.
Thank you, Sean.
I'll also just jump in and say, as the water supply becomes more constrained with higher use, we need our models to perform better. And that's one of the reasons we're sort of hoping to utilize as much satellite data as possible moving forward.
Mm-hmm.
Great, thank you. Question 5 is, what is the feasibility of using MODIS Terra and MODIS Aqua to study the Antarctic area? How to treat data?
Yeah, so, as you move towards the polar regions, the sun is lower in the sky. So it can be more challenging to use these optically based satellites to estimate, snow surface properties like snow cover, snow albedo, and other things. The models we have do account for the lower sun angle. So spectral mixture models use different spectral libraries to account for that lower sun angle. And the NDSI method divides by the sum of the reflectance in the two bands that are used to sort of account for the fact that it's a bit darker there. So the data is usable in these regions, but there's often, periods of very low light, which could be edge cases. And then, of course, there's periods where, there's 24-hour darkness or just darkness when the satellite's going over, if it's early in the morning. MODIS Terra goes over at 10:30 in the morning, and MODIS Aqua goes over about 1:30 p.m. So Aqua could be better for some of those edge cases, mid-season before the sun's a bit higher in the sky. So yeah, I think, and there are some studies showing the accuracy of these methods as well. I will try to add that study to this question as well. Thank you.
Wonderful. Thank you so much. Thank you, Karl and Sean, both, for today's presentations and answering all the questions. We're almost at the end of our webinar time, and so we thank everyone for attending this session, and once again to all our guest speakers. Also want to thank our ARSET team, our coordinator Selvin Hudson-Odoi and Brock Blevins, then editors Sue Monty and Jonathan O'Brien, and our helpers Sarah Cashel, Maria Marabito, and Natasha Johnson Griffin. So on behalf of myself and Sean McCartney, we thank you all for attending this webinar series, and we hope to see you in our future training. Please join our listserv through the email address provided. And just one more note about a survey that you will receive by email. At the end of each training, we do send a survey out to get your feedback, how we can improve, what else can we include, or what different topics that you might like to see in our training. So please take a few moments to complete the survey when you receive it. And thank you all again.